Okay, welcome to this video where we're going to be going over the 2000 AP Calculus exam. So without further ado, let's get started on question 1, where we're going to have this shaded region R in the first quadrant, bounded by this top graph, y equals negative x, e to the negative x squared, and this bottom graph, 1 minus cosine of x. So in part A, we're asked to find the area of region R. And the first step in finding this area is we need to know the x-coordinate of this intersection point here, because that's going to give us one of the limits for the integral. And the way we're going to figure that out is by setting the two equations that we have equal to each other. So we'll have e to the negative x squared being equal to 1 minus cosine of x, and this is going to be solved in your calculator by letting this equal to y1 and letting this equal to y2, graphing them, and then finding where they intersect. And if you do this, you'll get x being approximately equal to 0.942. Now we don't want to use this approximation for the rest of the problem, because that might lead to some small inaccuracies down the road. So what we're going to do is we're going to take the exact value of x and store it in the value a. So from now on, for the rest of this problem, whenever we need to use this intersection point, which is going to come up a lot, I'm just going to use the variable a, which you should have stored in your calculator. Okay, so now that we know this intersection point, I'll label this as a. We can now focus on finding the area. Now remember, the formula for the area is the integral from 0 to a, in our case, because we're starting at 0 and we're going to a, of the top curve minus the bottom curve. In our case, the top curve is this e to the negative x squared, so I'll put that here, minus, and then the bottom curve is the 1 minus cosine of x. 1 minus cosine of x dx, and then since you have the value of a stored in your calculator, this can just be plugged in and the calculator will give you the answer of being 0.591. You get 1 point for this problem for doing the integrand correctly, and you get a second point for getting the right answer. Okay, and then for part B, we're asked to find the volume of the solid generated when the region R is revolved about the x-axis. So since the entire of this bottom curve is not touching the x-axis, that's a signal that we're going to have two different radii. We're going to have the small radii from the x-axis to the bottom curve, and we're going to have the top radii, or the big radii, going from the x-axis to the top curve. Okay, so the small radius, I'll label that lowercase r, goes from 0 to 1 minus cosine of x, so the distance is just 1 minus cosine of x. And for the big radius, it's going to be going from 0 to e to the negative x squared, therefore the big radius is e to the negative x squared. Now that we know those two radii, we can plug it into the equation. Remember, the equation is pi times the integral from, again we're going from 0 to a, and we're going to do big R squared minus little r squared dx. So in our specific case, that's the pi times the integral from 0 to a of, well, big R is e to the negative x squared, that's squared, minus 1 minus cosine of x squared dx. And again, this is going to go straight in your calculator, and you will get an answer of 1.747 as your answer. You'd get 2 points for doing the integral correctly, and 1 point for the correct final answer. Okay, now looking at part C, we have that the region R is the base of a solid. For this solid, each cross-section perpendicular to the x-axis is a square. Find the volume of the solid. So what that means is we have a bunch of, that's the wrong color, that's not what I meant. We have a bunch of squares, like so. Right, if you can like imagine this three-dimensional shape that's being created here, we have an infinite number of these squares, and if you look at the length of each square, or the length of the side here, it's the top curve minus the bottom curve, right? It's the distance in between these two curves. So if we want to write an equation that'll give us the length of the side of the square, that's going to be this top curve, which is e to the negative x squared, minus the bottom curve, minus 1 minus cosine of x. Right? You can think about it as the top curve being this total distance, and the bottom curve being the extra distance that we don't want. So we're subtracting the extra distance that we don't want to get the side of the square. So this is the side of the square. And we want the area of the square, right? To be able to integrate it to get volume. So if you have a side of a square and you want to get the area of the square, you should remember from geometry that you just have to square it. So I'll take this quantity here, right, and then I can just square it, which will give me the area of one square. Right? If I give you one x value, you can tell me the area of that one square. But I want to find all the squares, right? The total volume that you get when you add up all the infinite number of squares from 0 to a. So we're going to integrate from 0 to a, and then we're just going to take this stuff that we got here, e to the negative x squared minus 1 minus cosine of x, add the parentheses, squared dx, and then again, this is going to go straight in the calculator, and we're going to get an answer of 0.461. Again, 2 points for the integral, 1 point for the answer, and for this whole question, like for all the parts, if you included the correct bounds of integration at least once, so in either part A, B, or C, if you put 0 to a, you would get one extra integral limits point, I guess. Okay, so now with that done, let's move on to question number 2. Okay, let's look at question 2 now. I'm sorry if this is really small, it's just that there's a lot of text and I have to figure out a way to leave some space. If you can't read this graph, this says time in seconds, this says velocity of runner A in meters per second, and this is 0.3 comma 10, and this is 10 comma 10. Okay, with that out of the way, let's look at the question. We have two runners, A and B, that are running on a straight racetrack for 0 is less than or equal to t is less than or equal to 10 seconds. The graph above, which consists of two line segments, 1, 2, shows the velocity in meters per second of runner A. So this is the velocity graph measured in meters per second. The velocity in meters per second of runner B is given by the function v defined by that. So for part A, we want to find the velocity of runner A and the velocity of runner B at time t equals 2 seconds, indicate units of measure. Alright, so runner A. We have this velocity graph, so if we want to find the velocity at time t equals 2, we need to go to x equals 2, or t equals 2, and try to find the point. And it's not really exactly on a whole number, so the way we're going to do this is by looking at the slope. We know that it goes from 0, 0 to 310, so the slope of this line segment here is delta y over delta x, which is 10 over 3. So every time I go over by 1, I'll go up by 10 thirds. So if I go over by 2, I'll go up by 20 thirds. Therefore, at x equals 2, y is equal to 2 times 10 thirds, which is 20 thirds. And then for runner B, we know his velocity function, so I can just plug in t equals 2 into his velocity function to get v of 2 being equal to 24 times 2 over 2 times 2 plus 3. Right, that's my answer for part A for runner B. And then for both of these, I should include units, and the units for velocity were given up there as meters per second. So I can put meters per second there. I'm just going to label this is runner B, and this is runner A. Brilliant. And you'd get 1 point for getting runner A correctly, and another point for getting runner B correctly. Okay. Now let's look at part B of this question. Find the acceleration of runner A and runner B at time t equals 2 seconds, include units of measure. So, part B. The acceleration of runner A, now the derivative of velocity is acceleration, so if we want to find the acceleration of runner A, we're going to be looking at the slope of this line, because the slope is the derivative. It's the rate of change. So the acceleration of runner A at time t equals 2 seconds is the slope of this line segment. In part A, we already determined that the slope of this line segment is 10 thirds. So the acceleration is the slope at x equals 2, which is 10/3. And then for runner B, the acceleration is again the derivative of velocity, but now since we have an equation, we have to take the derivative of this using the quotient rule. So the acceleration is the derivative of velocity v prime of t, which is going to be the bottom 2t plus 3 times the derivative of the top 24 minus the top function 24t times the derivative of the bottom, which is 2, all over the bottom squared, all over 2t plus 3 squared. And now we want to find the acceleration at time t equals 2, so that's simply going to be taking our derivative and plugging in 2, which is going to be 2 times 2 plus 3. Again, don't waste your time simplifying this, please. Even if it takes only like 30 seconds, there's a chance you could get something wrong, and there's no reason to take that risk. Just to get a near looking answer. Over 2 times 2 plus 3 squared. Okay? If you did happen to evaluate this, you would get 72 over 49, but we're not going to do that because that's no point. There's no point. And then for units. So to find the units, we want to take the units for our y-axis of the graph and divide it by the units of the x-axis for the graph. So the units for the y-axis are meters per second, and then the units for the x-axis are seconds, so we're dividing this by seconds. So you get meters per second, or meters per second squared. If you've taken any kind of physics class, that should be, if you missed that, I'm ashamed of you. Okay, so we can just write meters per second squared here. And I'll just label this A and this B. And again, you get 1 point for getting the correct acceleration for runner A, and another point for runner B. Okay, let's look at part C. So we have to find the total distance run by runner A and the total distance run by runner B over the time interval 0 is less than or equal to t is less than or equal to 10 seconds. Indicate units of measure again. So for part C, the total distance run by runner A is going to be the area under the velocity time curve, or the velocity time graph, or whatever. The keyword distance here, distance is the integral of velocity. If they'd asked for displacement, we would have had to take the integral of speed, which in this case it would have been the same, but it isn't always. So make sure you keep track of these keywords, distance correlating to velocity, while displacement correlates with speed. Okay? Anyways, to find the total distance from runner A, we're going to have to take this area under this graph from 0 to 10, like so. And that's going to consist of this triangle here plus this rectangle here. Right, that's going to be the front area of the triangle is going to be 1/2 times the base, which is 3, times the height, which is 10. And then we're going to add to that this base here, which is 10 minus 3 is 7, times the height, which is 10. Again, not going to evaluate that. That's all. This is for. And then for runner B, this is a little bit easier. We don't have to actually evaluate the integral like by hand. If you would use a u substitution, but there's really no point. We're going to go from 0 to 10 of the velocity function, which is 24t over 2t plus 3 dt. And this comes out to be 83.336 meters. And the way we got meters as our units is because when you're dealing with distance, when we're taking the integral of this velocity time graph, the way we find the units is by multiplying the units for the two axes. So this is for any integral in general. If you know the units of the axes and you want to find the units of the integral, we should multiply these two. So we'd have meters per second times seconds, because it's there, and the seconds will cancel out, leaving us just meters for our units. Alright, so that was part C. You'd get 1 point for the runner A, you get 1 point for the integral for runner B, 1 point for the answer for runner B, and for this whole question in general, if you got all the units, that would be 1 extra units point. Okay, that was question number 2. Now let's move on to question 3. Okay, so question 3 here. This is probably as simple as a question as you're ever going to get on an AP exam, so this is a pretty good one. We have a derivative graphed. We have the graph of f prime of x, and we're asked a bunch of different questions about f. Okay, so to answer this question, you really need to know the connections between f, f prime, and f double prime. Okay, so in part A, we need to find all values of x on this interval. So notice for all the questions, this is from -7 to 7. That's just talking about this area. So we want to find all the values of x for which f attains a relative minimum. So what a relative minimum is f prime of x is going from negative to positive. If you want to visualize that, you can think of it like this. We have a negative slope here, we have a positive slope here, and this point is clearly the minimum. Okay, and so on our graph of f prime, where does f prime go from negative to positive? Where does it cross the x-axis from the bottom to the top? And it seems like the only place where this is happening is here at x equals -1, where from before x equals -1 it's negative, and then after it it's positive. So x equals -1 is a relative minimum, and it looks like that's the only relative minimum, because there's no other points on the graph where the derivative switches from negative to positive. So we'd say x equals -1 is a relative minimum. And notice that they're not asking for the value of the relative minimum, they're asking for the x value where the relative minimum occurs. So we don't need to find x of -1, we just need to find -1. Okay, and then for the justification, you'd say x equals -1 is a relative minimum because f prime of x changes from negative to positive at x equals -1. Okay, and then part B, very similar. They switched out the word minimum for maximum. So at a relative maximum, f prime of x, instead of going from negative to positive, this time it's going to go from positive to negative. So where does the graph of f prime of x go from positive to negative? And again, that's only happening at one place, at -5, right? Here it's positive, here it's negative, so it's the only place where it's switched like that. So we can say x equals -5 is a relative maximum, and then for justification, you'd say f prime of x changes from positive to negative at x equals -5. And for both of these parts, part A and part B, it's 2 points. 1 point for correctly finding the either x equals -1 or x equals -5, and then you get another point for the justification. So 2 points in part A, 2 points in part B. Part C, find all the values of x where the second derivative is less than 0. So here's where the second derivative comes in. And you should know that the second derivative is less than 0 when the first derivative has a negative slope. That's the key idea here. So we have a graph of f prime of x, and to find out when the second derivative is less than 0, we just need to look and see where on this graph does f prime of x have a negative slope. Okay, so clearly starting here, going down, we have a negative slope, and then at 3 it becomes positive, and then now you have to be really careful, because notice how it says it has a vertical tangent line at x equals -3, or x equals +3, excuse me. What that means is that at x equals 3, the slope is undefined. So we can't say that the second derivative is less than 0 at x equals 3. But everywhere around x equals 3, from 2 up till just under 3, and then 3 to 5, So every single point like surrounding 3, so from 2 to just under 3, and then from just over 3 to 5, it's decreasing there. So writing that out in some notation, we'd get -7 to 3, -7 to 3, with parentheses, not brackets, and then from 2 to 3, and then from 3 to 5. It's really important to like show that's going from 2 to 3 and then 3 to 5, because this excludes the exact value of 3, like we wanted. This is also 2 points, 1 point for the -7 to 3 part, and another point for separating this 2 to 5 into 2 different things. Okay, and then part D, at what value of x for -7 is less than or equal to x is less than or equal to 7 does f attain its absolute maximum? Okay, so a good strategy for absolute maxima is absolute maxima or minima, just absolute extrema in general, is you want to set up like a table with a bunch of different x values on it. And the x values that you're going to want, first we're going to include the endpoints. So x equals -7 and x equals 7. And then we're going to include all the critical numbers for f. So remember, the critical numbers are when the derivative is 0 or undefined. So that's going to be x equals -5, x equals -1, and x equals 5, I guess. So now let's think about what an absolute maximum means. Okay, so remember, so when we're looking at the absolute maximum of f, that means we want f to be as large as possible. And then let me just erase this. So when we're talking about the graph of f prime of x, f is the area under the graph. So to find the area, to find like a value of f at a certain point, we take the area under the graph. So when we want to find f's absolute maximum, we want to find when the area under the graph is the maximum. So knowing that, we can start to eliminate some of these options here, because it's one of these, but we don't know which one it is, right? So clearly, we can eliminate -7, because at -7 the area is 0, and the area definitely gets bigger after 0. So we can eliminate this, and then when we're looking at x equals 5, starting at -1, the area gets bigger and bigger and bigger and bigger, and then it goes to 5, and it gets bigger and bigger and bigger again. So we know that 5 can't be the biggest, because 7 is bigger than 5. So we can get rid of 5. And then x equals -1, that's a relative minimum. So if it's a relative minimum, there's no way it's an absolute maximum. So we can get rid of that. And now we're left with x equals -5 and x equals 7. Okay? And just looking at this like graph and making a reasonable assumption, this is the area for -7 to 5. And then this is the, let's do green. So this is the area for -7 to 7. And it's clear that even though there's a small negative section, the total net area is way, way bigger for the green, for the green section. So for x equals 7. So the area under the curve is greater for x equals 7 compared to x equals -5. And therefore we'd say x equals 7 is where the graph attains its absolute maximum on the interval -7 to 7. And then for justification, we'd say, well, x equals -1 is a relative minimum. X equals -7 is not an option because its area is 0, and there's areas on the graph with the positive area. We can eliminate x equals 5 because the graph is continuously positive from -1 to 7. And then looking at the graph, it's clear that at 7 the area is greater than at -5, so therefore x equals 7 is the x value for which f attains its absolute maximum. Okay, this was a 3-point question. You'd get 1 for like making a list of these candidates and identifying x equals -5 and x equals 7 as the only reasonable options. You'd get 1 point for stating that x equals 7 is greater than x equals -5. and then you'd get another point for the proper explanation of that. Alright, so that was question number 3. Now let's move on to question 4. Okay, so question number 4, we have water that's going into an underground tank at 8 gallons per minute, water coming out of the tank at square root of t plus 1 gallons per minute, and at the initial time t equals 0, the tank contains 30 gallons of water. Okay, so part A asks, how many gallons of water leak out of the tank from time t equals 0 to t equals 3 minutes? Alright, so when we are dealing with water coming out of the tank, the relevant expression in the paragraph here is the square root of t plus 1 part, because that's talking about how much water is leaking out of the tank. But if we just plug in like a specific t value, that's going to tell us how much water is leaking out of the tank at that specific time. But we want to figure out how much water is leaking out of the tank in total for like all the t values combined from 0 to 3 minutes. And that kind of a question just screams integration. So it should be a pretty straightforward, thought that you should integrate this from 0 to 3, because we're going from t equals 0 to t equals 3 minutes. And if we integrate this expression here, that gives us the amount of water leaking out at a specific time, and we do it for all the times from 0 to 3, this should get us the total amount of water that's leaked out from 0 to 3. And now that we're in question 4, this is the no calculator section, so we're not going to be able to just put this in a calculator. But thankfully the integral is not that hard to do. First, I'll just rewrite the square root as this being raised to the 1/2 power. And then you don't have to do a u sub here because the coefficient is 1. But if you want to do it because it makes you feel good, by all means go ahead. This will get you 2/3 times t plus 1 to the 3/2 from 0 to 3. Because we raised the power by 1 and multiplied by the reciprocal, and then now the bounds are still 0 and 3, and if I plug in 3 and I plug in 0, I'll get 2/3 times 4 to the 3/2 minus 2/3 times 1 to the 3/2. Okay, and that's it for part A. This was a 3-point question. You get 1 point for the correct bounds of the integration of integrals. You'd get another point for the square root of t plus 1 part inside, and you'd get a 3rd point for a numerically correct answer. Okay, part B, how many gallons of water are in the tank at time t equals 3 minutes? Well, we know that the total amount of water in a tank at any given time, if we're just thinking logically about this and just ignoring all the math, at any given time it's going to be the water at the start plus the water coming in minus the water going out. And what's nice is we have values for all 3 of these things. So we just have to plug in the values and plug in time t equals 3 and see what happens. So at the start, we're given that at time t equals 0, the tank contains 30 gallons of water. So this value is 30. And then the water in, we know that the water is being pumped into an underground tank at a constant rate of 8 gallons per minute. So at 3 minutes, there's going to be 8 times 3 gallons of water in. And I'd even tell you, don't simplify the 8 times 3. Maybe you're going to make a really silly mistake. There's no point taking a risk. And then water out, well, we already did the integration to find out how much water has gone out of the tank in the first 3 minutes, and we got 2/3 times 4 to the 3/2 minus 2/3 times 1 to the 3/2, right? And then this would be the final answer there. So for points, this would be a simple 1-pointer because there wasn't that much to it. Yeah? And then what happened there? I don't know what happened. So part C, what the heck is going on? So part C is, we're going to still use this water at start plus water in minus water out thing. Okay, so we have a expression a of t for the total number of gallons at time t. So now we just took this, we did the specific case of time t equals 3 minutes in part B. Now we're going to generalize this for any time t. So the water at the start, we know that's always going to be 30 gallons, right? Regardless of the time. That's always going to be 30 plus, and then the water in, it's 8 gallons per minute. So for at t minutes, there's going to be 8 t gallons of water in the tank. And then for water out, remember we did the integral before, and we went from 0 to 3 because it was from 0 minutes to 3 minutes. Well, now since we don't know a specific time, we just have t, we're going to go from 0 to t. And I'm just going to switch the variable here to x instead of t, just to make it a bit clearer that this t has nothing to do with the stuff that's inside. Okay, and then that's it, right? Now if someone wanted to find the amount of water in at a specific time, they could just plug in the t value into this expression and get the total amount of gallons of water in that tank for that specific t value. And this is a 2-point question. 1 point for this 30 plus 8t stuff, and another point for subtracting this integral. Okay, and then part D, at what time t is the amount of water in the tank at a maximum? Justify your answer. So when the amount of water in the tank is at its maximum, then we're gonna have, remember how a of t was our expression for the amount of water in the tank? If we want that to be a maximum, then we want to find a prime of t, right? And set that equal to 0. So first let me rewrite a of t, and then we'll see what we can do from there. Okay, so now that I wrote down a of t, we want to find out when this expression is at a maximum. So we're going to take the derivative of this, a prime of t. And if we do that, the 30 goes away, the 8t becomes an 8. And then we're taking the derivative of an accumulation function, so it's just going to be the square root of t plus 1. And we want to find out when this is 0, right? Because that's when it's at a maximum, a critical number. So on a new line, remember it's really important to do this minimum and maximum stuff on a new line. 8 minus square root of t plus 1 is equal to 0. Square root of t plus 1 equals 8, right? Adding it to both sides. And then taking the square, both sides, t plus 1 is equal to 64, and subtracting 1 to get t is equal to 63. And just a real quick check, that is in between t equals 0 and 120, so we're good on that front. And then now we just need to make sure that this is actually a relative maximum and not a relative minimum. And the way that I'm going to choose to do that is by using a number line. Plugging in 63, and going back to our a prime of t function, if I plug in a number greater than 63 here, it's going to be negative. And if I plug in a number less than 63 into t, this is going to be positive, which means the graph is going up, 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 and then it's going down, down, down. So this is indeed a relative maximum. So remember, they also asked us to justify our answer to show that 63 is the maximum. So we did something like a prime of t is positive for 0 is less than t is less than 63, and then negative for 63 is less than t is less than 120. Therefore, the maximum is at t equals 63. Alright, and then this is a 3-point question as well. We'd get 1 point for taking the derivative and setting it equal to 0. You'd get another point for solving this expression and getting t equals 63. And then a 3rd point for the correct justification, showing how the sign switches from positive to negative. Okay, so now let's move on to question number 5. Okay, now let's look at question number 5. So we have this curve given by that equation there. And in part A, we need to show that dy dx is equal to this here. So what they're asking us to do here is to take the derivative and then show that the derivative is this. So they're giving us the answer, really. We just have to do it and do it ourselves and check that this is right. So let's take the derivative of this expression. And since we have y's and x's all mixed together here, this is going to be implicit differentiation. Okay, so let's focus on the xy squared part first. So if I take the derivative of this using the product rule, I'm going to have y squared times the derivative of x, so y squared, plus x times the derivative of y squared, which is going to be 2x y, and then the derivative of y is going to be dy dx by the chain rule. And then now that's that part, now let's focus on the x cubed y part, minus, and then so we're going to do the same thing here. We're going to keep the y and take the derivative of the x cubed, which is 3x squared y, and then we're going to add to that x cubed times the derivative of y, which is dy dx, and that's equal to 0, right, because the derivative of a constant is 0. And now we just have to solve this equation for dy dx. So let's first start by distributing the negative. I'll write my y squared, my 2xy, minus 3x squared y, minus x squared dy dx, 0. Don't forget that the negative goes to both of the things here. I feel like a lot of times when you make a mistake, it's not a calculus mistake, it's actually an algebra mistake. So we're going to watch for these like small details that might cost you some points, yeah? So now that we did that, we can bring all the things, so now we can take like this term and this term that doesn't have a dy dx in it and bring it to the other side. So we'll have 2xy dy dx minus x cubed dy dx being equal to, if I bring this to the other side, I'll get 3x squared y, and if I bring this to the other side, I'll get negative y squared, right? Now let's factor out the dy dx here. That was the reason we brought those other terms to the other side of the equation. So if I factor that out, I will get 2xy minus x cubed being equal to this stuff. And then the final step is to divide by 2xy minus x cubed. So we're solving for dy dx, remember? And that gets us 3x squared y minus y squared over 2xy minus x cubed, right? That's our answer. Let's check that that's what we had in part A that they give us. 3x squared y minus y squared, 3x squared y minus y squared, and then 2xy minus x cubed, 2xy minus x cubed. We did that part right. And this is a 2-point question. You'd get 1 point for doing this, the implicit differentiation, and you'd get a second point for doing the solving for dy dx part correctly. Okay, now let's erase this and move on to part B. Alright, in part B, it says, find all points on the curve whose x-coordinate is 1 and write an equation for the tangent line at each of those points. Okay, so the x-coordinate is 1. That means on this curve, x is going to be equal to 1. So let's find all the possible values of y when x is equal to 1. So we'll plug in 1 into this equation. In that case, we'll get 1 times y squared minus 1 cubed times y equals 6. So we'll get y squared minus y equals 6, or y squared minus y minus 6 equals 0. And then this will get us y minus 3, y plus 2 equaling 0. And then y is therefore equal to negative 2 and 3, right? So since x is equal to 1, we've now got 2 points. We have 1 comma 3 and we have 1 comma negative 2, right? So let's get started by writing tangent lines for each of these two, right? So the tangent line is going to be the point plus the slope. So we have the point, we need to find the slope. Let's start with 1, 3. We need to find the slope of the line at 1 comma 3, and to do that, we're going to use the differential equation they gave us. So I'll just write it over on the corner here, just like as a side note so we can reference it later on. I don't have to keep going up and down. Dy dx is 3x squared y minus y squared over 2xy minus x cubed, right? So now I'll just plug in 1 and 3 into this, and then we'll see what happens, right? So that's going to be 1 So it's going to be 3 times 1 times 3 minus 3 squared is 9 over 2 times 1 times 3 minus 1, which is 3 times 1 times 3 is 9. 9 minus 9 is 0. So it's 0 over 5, which is 0. Okay, so if I wanted to write my equation in point slope form, that's going to be y minus y1 equals m times x minus x1. You don't really have to simplify this to equal y equals 3. That's good enough. And then now we'll do the same thing for 1 comma negative 2. Okay, it's going to be the same thing, but instead of plugging in 3, we'll plug in negative 2 into dy dx. So we'll have 3 times 1 times negative 2 minus negative 2 squared is positive 4. Careful with the signs there. And then 2 times 1 times negative 2 minus 1, which is going to get us negative 10, because you have negative 6 minus 4, over negative 4 minus 1 is negative 5, and that's a positive 2. So this is our slope for 1 comma negative 2. Therefore, writing my point slope form, I'm going to get y minus a negative 2, so plus 2 equals m, slope 2, times x minus x1, 1. That's my second point, or second equation. And then this is a 4-point question. You'd get 1 point for writing this equation and solving it for, or you're writing an equation in terms of y. You get a second point for solving for y correctly and getting negative 2 and 3. And then the scoring guideline says you get 2 points for the equations. I'm not exactly sure if it's 1 per or just 2 for both of these combined, but either way, you get 2 for these, 2 for the first part, and that's a total of 4 points. Now let's move on to part C. Okay, part C, find the x-coordinate of each point on the curve where the tangent line is vertical. So when the tangent line is vertical, the slope is undefined, right? Because the tangent line is going to look like that, and the slope of a vertical line is undefined. Okay, so we want to find all the points where the slope is undefined. And here's our slope. If we want to find out when is this undefined, well, the derivative is going to be undefined when the denominator equals 0. Right, so if this part, the bottom, equals 0, then the slope is undefined. So what we're going to do there is we're going to take 2xy minus x cubed and set it equal to 0. And this is going to give us all the coordinates, x comma y, where if you plug that into your curve, you'll get a horizontal tangent line at that point. Alright, so how do we solve this? Well, let's start by factoring out an x. So we'll get x times 2y minus x squared equaling 0. And that's going to give us x equals 0. And then y is equal to 1/2 x squared. Okay, so what we're going to do now is they want the x coordinate for this point, right? So we already have the x coordinate here, but we're going to plug it back into the curve just to make sure that it's a valid point, because you might get an extraneous solution, right? So if we plug x equals 0 back into the curve, that's going to give us 0 times y squared minus 0 times y equaling 6, which is 0 minus 0 equaling 6. And does 0 equal 6? Well, I don't think it does. So that means there's no y coordinate rather, where x is equal to 0. So x equals 0 is not a valid solution, because whenever x is 0, there's not a corresponding y value on the curve at all. So x equals 0 is not a valid solution. We can cross that off the list. Okay, now we're left with y is equal to 1/2 x squared. So when y is 1/2 x squared, we can take this and plug that back into our curve again, so that we'll only have everything in terms of x's, right? So that's going to be x times x squared over 2 squared, x times, this is our y, so y squared, minus x cubed times y, so x squared times, or x cubed times x squared over 2, and this is equaling 6. Okay, so now if I expand this out, I'll get x to the 5th over 2 squared is 4, minus x to the 5th over 2. Remember, when you multiply two things with the same base with different exponents, you add the exponents. And then this is equal to 6. I can simplify that a bit, simplifies a bit more, and I'll get negative x to the 5th over 4 equals 6. And then, and then x to the 5th equals negative 24. Therefore, x is the 5th root of negative 24, like that. And then in terms of points for this part, you'd get 1 point for setting the denominator equal to 0. You'd get another point for substituting the x squared over 2 in for y. And then you get another point for solving for the proper x coordinate. Okay? And one other thing to mention real quick, if you wanted to, I feel like this is a bit of a longer way, but you could also solve this for x, substitute that into the equation to solve for y, and then solve that, and then take your y value, plug that back into the equation to solve for x. That's just an extra step, but it is mentioned in the scoring guidelines, so I thought I'd mention it real quick as well. Okay, so that was the conclusion of question number 5. Now let's move on to the final question, number 6. Okay, so question number 6, we have a differential equation. dy dx is 3x squared over e to the 2y. And in part A, we need to find a solution to the differential equation satisfying f of 0 is 1/2. So sometimes the AP, they'll give you this kind of thing, this f of 0 is 1/2. And you need to be able to recognize that what this means is that the point 0, 1/2 is on the solution. They're not going to give you 0, 1/2. Sometimes they will. Sometimes they'll give you this f of 0 is 1/2. But you have to be able to recognize that these are the same thing. Okay, so now let's take a look at part A. So we need to solve this differential equation. Now on the AP, the only way that you'll need to know how to solve these equations is by separation of variables. So we're going to do that by taking all the y's on one side and all the x's on the other side. So the way we're going to do that is by taking this e to the 2y and bringing it over to the y side, and this dx and bringing it over to the x side. If we do that, we're going to get e to the 2y dy is equal to 3x squared dx. And then now we can take the integral of both sides, and then that's going to give us, well, if we take the integral of this, you can do a u substitution if you want, but by now you should really be able to do this kind of stuff in your head. You're going to get 1/2 e to the 2y, and then over here we're going to get x cubed plus c. Notice how I didn't include a plus c on this side too, because when you're solving a differential equation, you really only need one constant. Since if there was a constant here, you could just bring that to the other side, and then you'd have one constant anyways. So now we can start by solving this whole equation for y. We'll start by multiplying everything by 2. We'll get e to the 2y is 2x cubed plus c. And then again, notice that how the c, it didn't turn into a 2c, because if you multiply a constant by a 2, it still remains as a constant. Okay, I'll do it here again. So now, on our path of solving for y, to get rid of this exponent here, we'll take the natural log of everything. And then the natural log of e to the 2y is just 2y. And then the natural log of this, I'll write that out. The natural log of 2x cubed plus c. And then finally we'll divide by 2 to get y is the natural log of that over 2. Now, are we done yet? Not quite. Why, you ask? Well, we need to figure out a solution that satisfies this. So 0, 1/2 is on the curve. How do we figure that out? Well, we take 0 and 1/2 and we plug it in for x and y, and then we'll solve that and see what happens and what value we get out for c. If we plug in 0 in for x and 1/2 in for y, we'll get that 1/2 is equal to the natural log of 2 times 0 plus c over 2. Okay? And then this 2 is going to cancel with that 2. So then we'll be left with 1 equaling the natural log of 2 times 0 is 0. So 0 plus c is c. So this is just the natural log of c. And then now to solve this, we can raise everything to the e power. And we'll have e to the 1 is just e equals e to the natural log of c. Well, e and the natural log are just going to cancel out. So we'll just get c. So we solve that the value of the constant c is equal to e. Therefore, in this original expression here, I can just replace the c with e. Okay, so I'll write it down here. Let's do it in pink. We'll have y. Nope. We'll have y is the natural log of 2x cubed plus e over 2. Okay, and despite this being a relatively straightforward question, this was actually worth 6 entire points, which I find really interesting. So you get 1 point for separating the variables by bringing the y's to one side and the x's to the other side. You get 1 point for correctly integrating y, another point for correctly integrating x, another point for including a plus c here. So all the way, we haven't even done any of the real math yet. We've only done a couple basic steps, and we're already at 4 points. So you could just do this, and you'd already have 4 out of your 6 points for this question, or for this part. And then you get another point for correctly solving for the value of c, and then finally for putting that in here and solving the whole equation for y. That's another point. That's a total of 6 points, right? Now let's move on to part B. Okay, so part B, we have to find the domain and range of the function that we got in part A, and just for convenience, I've copy pasted the function here. If you don't really know, I really love copy and paste. So anyways, we need to find the domain and range of this function. So the key aspect of this is this natural log here. That's going to be what's dictating the range and the domain. Okay, so we know that this stuff that's in here has to be, like, we should be able to find the natural log of it. And you should know that if you want to find the natural log of something, it has to be greater than 0. So you can't take the natural log of 0. You can't take the natural log of negative numbers. So for this function, natural log function to be defined, this stuff that's in here has to be greater than 0. So 2x cubed plus e has to be greater than 0. Okay, and then if we solve this, x cubed is greater than negative e over 2, and then x is greater than negative e over 2 to the 1/3 power. That's our domain, right? X can be any number that's greater than this. And remember, this is just some numeric value that we don't know. And then now we need to find the range of this function. Well, let's look at it, right? So what is the range of the natural log function? So the range of ln x, or I'll just write ln. The natural log function, that goes from negative infinity to infinity, right? If you take the natural log of like a really small number that's just over 0, that's going to be like negative, it's going to approach negative infinity. And then if you take the natural log of larger and larger numbers, the value is going to approach infinity. So the range of the natural log is negative infinity to infinity. And then therefore, since this function goes from negative infinity to infinity, and the 2 isn't really going to change the range or domain, or it's not going to change the range, excuse me, the range of the entire function y is also going to be negative infinity to infinity. Right, so the range of y is negative infinity to infinity as well. want to write that at negative infinity less than y less than infinity. You don't want to include the equal, less than or equal to, because it's just like, I don't know, just gets kind of weird. So just leave it like that. Negative infinity is less than y is less than infinity. And then in terms of points for this, you'd get 1 point for setting the 2x cubed plus e being greater than 0. You'd get another point for solving that. And then you'd get another point for the range. Okay, so this is the culmination of the 2000 AB Calculus review video. I hope you found this helpful, and I'll see you in the next one. Goodbye for now.